In this second Proton NMR video, I'm going to look at higher resolution NMR spectra, and we're going to look at the extra information you can get from these spectra. So as well as knowing how many different proton environments we've got from the number of peaks and what type of environment it is from the shift value, you can also tell the relative number of hydrogens in each environment, and we can tell that from something called an integration value, so I'll be looking at those. And also you can tell the number of adjacent hydrogens from the splitting patterns, and this one here is what causes a lot of students some quite serious headaches. So we'll start off by looking at the NMR spectrum of ethanol. So you can see I've drawn up a displayed formula for ethanol, and I've shown the different hydrogen environments using these three different colours, green, blue and red. And there's roughly where these peaks would lie, their shift values. So we've got this hydrogen carbon bonded to another carbon, this environment here. So we've got a peak sort of between 1 and 2 ppm. The blue environment, hydrogen to carbon to oxygen, somewhere between 3 and 4. And remember, the OH environment's very broad, so I've gone for somewhere between 5 and 6. Now you'll notice that the peaks are now have a bit of area to them, whereas in the simplest type of NMR they're just straight lines. And so all the machine does is it measures the area underneath each of these peaks, and then it just ratios them. Now you may see the information that the machine generates in two different forms. I can remember having to teach these integration curves, and so the students would have to measure the vertical height of each step and then ratio them themselves, and I've tried to draw them in the ratio of 1 to 2 to 3. You might also simply just see the numbers on top of the peaks, and again it's been measured by integration by the machine, but it's rather than draw the integration curves, it's literally just giving you the ratios there. So that's 1 to 2 to 3 just in numerical form. So what that's telling you is the protons, or the protons in this environment, well, that's got the least amount of area. So it's saying, well, for every one of those there are 2 of those to 3 of those. And you can see in ethanol that these numbers actually refer to the actual number of hydrogens in each environment. And so in the red environment, the area of 1, well, that's because there's only 1 proton in this environment, 2 because there's 2 in this environment, and 3, there are 3 in this environment. So these are called integration values, and these tell us the relative number of hydrogens in each environment. In the case of ethanol, the integration values were the actual number of hydrogens in the environment, but that's not always the case, as you will see in a moment. So if you want to have a look at these two compounds, we've got 5 carbons in each. This is an aldehyde, so this is Pantanal, and this is the ketone, one of the ketones with 5 carbons, and this is pentanthreone. So ask yourself, how many environments have I got for the hydrogens, and what would be the relative peak areas or the integration values for each peak? So we'll start with Pantanal. We've got unique environments for every single type of hydrogen. So this is the only CH3 group in the molecule. So that's one environment. We've got a few CH2s, we've got 3 CH2 groups, but this is the only one bonded to a CH3 group, so that's its own unique environment. This is the only one bonded to the aldehyde group, so that's obviously a unique environment. And this is the only CH2 group with this environment on the right hand side and this on the left. And obviously that hydrogen there is totally unique as well. So 5 environments. So what are the relative numbers of hydrogens in each environment? Well, for every one of those, we've got 2 of those. For every one of those is 2 of those. For every one of those is 2 of those. For every one of those is 3 of those. So the peaks, the corresponding peaks for these protons would have 1, 2, 2, 2, 3 written above them. So if we look at pentan now, have we got 5 environments? Is every hydrogen in a unique environment? Well, we'll look at these hydrogens first of all. I'll use colour this time. So we've got this CH3 group. Now let's look at this CH3 group. Are these in the same environment as these? Well, just look at what they're bonded to. Of course they are, so we'll go for green for those. And then the hydrogens on the CH2 groups, we'll go for red for these. And are they in the same environment as those? Well, look at what's bonded to the left, look at what's bonded to the right, and of course they're equivalent as well. So we've got 2 environments. So if we think about the relative peak area, or the ratio of the areas of the peaks, so we've got 6 greens, so there's 6 greens to 4 reds. So that's a 6:4 ratio. Now that can obviously be simplified, so the numbers that would be drawn on the peaks corresponding to these protons would have the numbers 3 to 2 on. So we need to be careful that we don't automatically assume that the peak area is the actual number of protons in the molecule. So I'll go back to this statement here. The integration values tell us the relative number of hydrogens in each environment.